I'm Dan. I'm a runtime architect here at Oracle. I put this talk together with Yoy, who's unfortunately not here today, so you just stuck with me. And we're going to talk a little bit about Project Leyden. We're going to talk about Project Leyden's assembly phase, and we're going to demystify that a little bit. But to be able to do that, I want to take a little bit of a victory lap for a minute and look back. I love this slide because it's recursive. 2 years ago, Mark and John were here, and they talked about Project Leyden. They talked about the vision for what we're going to do with Leyden. They showed some of the prototypes, some of the different directions we had, talked about performance and the way that we were going to achieve these things. Last year, Yoy and I were able to stand up here and talk about the work that we were in the process of delivering, taking some of those prototypes, tuning them, redirecting them, and productizing them. And so we were able to take the first bit of work and ship that in JDK 24, and we've continued that process and been able to deliver more and more of that in each release that we've been able to do. So it's nice to pause for a minute sometimes and to look at these things and say, we laid out a vision and we've been incrementally walking our way along this and delivering on it. And along the way, we've been making things faster and start up quicker. Right? And so that, for those who aren't familiar with Project Leyden, and probably by this point in the conference, most people are, because we've talked about it in workshops and had references to it throughout different talks, but Project Leyden is really focused on two things. It's focused on making your application start quicker by speeding up startup and warmup. Now, startup and warmup are really poorly defined terms. Everybody's got sort of their own pet definition of what this means. But for the purposes of what we're looking at, we'll say startup is about how fast or how long it takes your application to do the first useful or meaningful piece of work. And warm up is then the time from doing that first piece of useful work until we hit our steady state of peak performance. So again, all three of these phases are somewhat fuzzy, but it gives us a bit of a working definition to use when we're trying to tune these things. It's important to note, though, that startup and warm up aren't just a JVM or just an application thing. It's both pieces connected together. During startup and warm up, there are things that are happening that your application's doing. You're parsing your configuration files. Maybe you're crawling the class path to find annotations to register beans or whatever it may be. And during all of this, the JVM's loading your classes and executing them and profiling them and doing all the work that we need to do. And in every run, we start as though it's a first run with no memory of what happened before. And the reason we do that is because Java is highly dynamic. It lets us drop new jar files in and continue executing. Now, normally here I talk more about static and dynamic, but John's going to give us a much more detailed and much better talk. I'm looking for where John is, but I'm sure he'll be here by the time of his slot, and he'll give us a much deeper view on that. So let's level set a little bit more on what we've been able to deliver. And in JDK 24, we brought in ahead of time class loading and linking. So we said the things that happen in one run are likely to continue to happen in later runs. So we're able to take the set of classes that you've loaded, we're able to record the relationships between them, we're able to record which constant pool entries you've resolved, and we're able to persist that in a way that we can use it in later runs to start you up quicker. Now, what does this get us? It gets us this. I took the standard sort of more common application servers and their getting started type APIs and ran them on a JDK 24 mainline build and then ran them with the JDK 24 AOTCache. And we get like a 2x, almost 3x improvement on these sort of simple applications for getting started with these different servers. And the point here is not to compare the servers against each other. It's just to see the difference between that orange line and that gray line. Now, what we delivered in 24 is not all of the things that we're working on. There's a lot of other pieces that are still in the Leyden repository. And so if we see that green bar, we see the further improvements we can do with those additional pieces. And we don't get a huge improvement with those additional pieces on the hello world type applications, but we do get a fairly good, almost 2.5 to 3x improvement on Spring Boot's Pet Clinic, which is a little bit larger, and so startup and warm-up are a bigger piece of that. So 24, we delivered a lot of the first foundational building block. And in 25, we're delivering the next foundational building block, the method profiling, being able to collect profiles in one run and use those in a later run. Now, there's a whole talk here I could go into on how the profiling works, the details of what we profile and how we record that. But the key thing is it's the kind of method profiles we take that we use to drive JIT compilation in a normal run, that we persist enough of that information so that we can reuse it to optimize and avoid having to do all that profiling work in a later run. Now, we spent a lot of time in the workshop earlier this week talking about different kinds of deployments, and people wanted give me one option that just makes things fast. And we heard you, but we didn't give you one option. We didn't take away the workflow we have. We simplified it a little bit. So we also added JEP 514 ahead of time command line ergonomics. And this makes it a little bit easier to use the AOTCache and to do the training run and the assembly phase. I'll talk more later and show the actual command line options and how things changed. But just to know that we have heard you, we are building the foundational building blocks, and we're trying to make them more usable and easier to use. But it's probably important to pause for a minute and talk about deployments. Hopefully everybody's familiar with the story of the blind wise men and the elephant, where they're very interested in seeing this elephant, and they're each taken to a different piece, and one holds the trunk and says, oh, elephants must be like snakes. And another holds the ear and says, elephants must be like, these must be like wings, so it must be some kind of bird, right? And each touches different parts of the elephant and comes to a different conclusion. And we're often like that when we look at our deployments. We say, guys, you're on the right track, but if you just turn it a little bit like this, it would meet what my deployment needs. But when we look, there's a whole bunch of deployments, and I'll just talk about a couple here. Maybe your deployment looks like some kind of horizontally scaling microservices where you want each subsequent one to come up quicker so it's ready to take load. Maybe your deployments are desktop applications, and you want your users to get that fast splash screen so they feel like your application's coming quickly so it's ready to take their first set of input. Maybe it's a command line tool, and you want it to spend more time processing data files than starting up the JVM. Maybe it's a framework, and you want to be able to deliver some kind of optimized version of your framework that starts your framework and gets that code loaded and ready to go, and so users can just drop their code on top and run on that faster piece so they're into their code sooner. Or maybe you're doing some kind of canary deployment where some canaries are able to spend some additional time to pay some extra costs to be able to do the training runs that we need to optimize things. Each of these scenarios wants the same sorts of things. They all want to get to peak performance quickly. They all want to spend as little time starting up and warming up as they can. Right? That's what Leyden's here for. But if we only focus on one of these deployments, we're going to miss the others. And so a lot of what we're doing is building the foundational building blocks, starting to get some workflows out, and trying to get you to pick them up and use them and try them and provide us feedback on where the rough edges are. But with a lot of these things, it's kind of like IKEA. There's a little bit of assembly required. Okay, so enough looking back and talking about what we have delivered and are in the process of delivering. We need to talk a little bit more about how Leyden works so we can start to demystify this assembly phase that I've mentioned a few times. And again, application performance, we're focusing on that sort of circled part of our graph. And part of this is that for many applications, they don't stay up as long as they used to. With continuous deployment type things, we start them up and shut them down and start them up much more often, so that startup and warm-up time is a bigger piece of the application's lifecycle. Now, JVMs are awesome, and they're awesome at optimizing code. And one of the key things that they do is they run your program to understand what to optimize. So we run it, and we observe what your program does, and we use that to drive which methods to compile, right? That's the name of hotspot. We find the hotspots in your program, and we optimize those. We find the paths through the code that you're running. We find the types that you're using. We find which call sites see which types, and we use that to continually optimize the application based on the observations that we've been able to make. Those optimizations are all speculative though, right? Our JIT compilers are great at saying, this past behavior should continue to hold, so we'll speculate that it does, and if it doesn't, we will have some kind of fallback, decompilation or something. So we continue to run, we don't have to rely on the optimization, we just use it to get good performance. Now, what we like though is that process of observation, speculative optimization, recovery paths, because we want to be able to use that just-in-time optimization and kind of shift that earlier. Now we don't want to say, okay, that was great for JIT compilation, we'll do something different for AOT. No, we want to say that JIT compilation, that whole process, really wants to be done ahead of time. So how do we take that observation, speculative optimization process and allow it to speculate across more than one run of your application? Well, the first obvious thing is we need to do something to observe your program, right? This is our training runs. And the best way to know what your startup and warm-up code is going to do is to run that code. That lets us know ahead of time what we would only be able to discover during runtime, right? This is our observation phase. So what makes a good training run? Well, the best training run is your application, right? Run it in production, record what it's doing, and use that as some kind of feedback loop to drive what we can optimize for you. Now, that may not always be possible. Depends on your deployment, depends on your environment. So the next best thing is something that exercises those warm-up and startup paths during your build pipeline or in some other way for you. Integration tests that are carefully crafted would be a good sort of candidate for this. And the key thing here is that training runs are effective, almost unreasonably effective, because they give us the same input and the same information that our JIT compiler would use. It gives us the observation of what is actually happening. All right, so we have a training run. We've used it to collect some observations. What happens after that? Well, in JDK 24, we have this 3-phase workload. And if you were at the workshop earlier this week, John talked about the early prototypes where it was actually like a 5-step workflow. So the fact that we were down to 3 is pretty good. And the way this works is in your training run, you say XX AOT mode record, and you record your observations into the AOT configuration file called app.aotconfig. Then you take that set of observations in that AOT configuration file and you run what's called the assembly phase. And in that we say our mode is create. So we're going to create a cache by reading the assembly phase, and we're going to write that out into the AOT cache called app.aot. And then our deployment run, we're going to run using that cache. Right? You've seen this before if you've seen other Leyden talks. But JEP 514 says maybe we can simplify this a little bit. Maybe we can take that training run and the assembly phase and sort of combine that by giving you only one option that you have to specify. We're not taking away the 3-phase workflow because that seems to work well for certain kinds of deployments, but we are trying to simplify things for some of the other kinds of deployments. And so in this model, you say, I'm going to create an output cache. So -XX AOT cache output, and you run your application. Now, this doesn't mean that the training run has disappeared. In all models, we still have that assembly phase. We've just either have it separate or it appears to be sort of glommed onto the end of the training run, but it's really 3 separate phases. And the reason we have this, and we'll get more details into this, is that we need a clean separation because it's really easy to cause ourselves problems by not having a clean separation. So why is an assembly phase needed? The whole point of what we've been doing is to make things start up faster and warm up faster. But if we're not careful, we're going to end up with a world where we have changed the meaning of your program. So we want to take our observations We want to use those from our training run, and we want to use them in our deployment run, but we don't want the deployment run and the training run to be intertwined in a way that changes what happens with your program. We want the results that you get out of this to be consistent, just get them faster. So we have this invariant that we've been trying to track, and that's that training runs and deployment runs should produce consistent results for consistent inputs, given consistent command lines and environments, right? If I run my AOTCache on the same machine and give it the same inputs, I should get the same outputs within realms of what your program actually does. But that means that we need some kind of clean separation, because otherwise we're going to leak state from that training run into our deployment run. And that state can leak through both at the JVM level and in the object heap level. So let's take a look a little deeper. You're probably asking yourself, like, guys, really? Why are you doing this way? It seems like it's an awful lot of work, right? We have the state at the end of the training. Why can't we just use that? And I don't know how many of you had scrambled eggs this morning, but it's really easy to take a set of eggs and to scramble them. I have yet to meet anybody or seen anything that can take that scrambled set of eggs and put them back into the original shells, or even other clean separations of shells. And that's really what happens when we run our program. We have a fairly clean set of class files, we have a clean set of our environment, and as we start to run things and load things and execute them, they start to become intertwined and intermeshed. It's really easy to end up with state that we don't want to record. Maybe our static fields cache some value. And maybe when you go to shut down at the end of your training run, you cache some state that says, hey, we're in shutdown mode, everybody shut down. If we captured that state and we tried to reuse it, the first thing you would do is immediately shut down because the state was telling you to. Maybe we captured a cryptography key in some way and you really don't want to persist that. Maybe we captured the clock, and so everything starts to time out because the clock that we captured is too long from something for what you're doing. So it's very easy to end up with crosslinks and state that we don't know what to do with. And besides that, maybe you captured some other piece of memory, some VM state, and you stored it along, and we don't know about it. Maybe we do know about it, but what do we do with it? Do we update it? Maybe we can, maybe we can't. Do we just reset it? Well, what happens about everybody who knows about that piece of state that you had? Can we maintain it? Maybe. There's really a lot of open questions of what we can do. So this is going to be a little bit provocative, but the object heap from our training run is kind of like a toxic asset, right? It really feels like it should be valuable. You're like, hey, you've built up all this state. I want to use that again. But that state isn't clean. It's non-reproducible. We can't guarantee that the state that you got this time is going to be the state that you need next time and that you're going to get the right set of inputs. Maybe there's a counter in there, and so with consistent sets of inputs to our training run and deployment run, we start producing different results. That's not what we want. We want to be able to use some set of state, some set of observations to be able to drive our optimizations. But the object heap itself may not be what we need. It's also typically, by the time you run for some period of time, much larger than you would actually want. And now you have to figure out which pieces of this do I carve off and not keep. Okay, so we're like, maybe it's just us JVM guys who have a hard time trying to clean your user application state. So let's say maybe there's a set of methods. And you as a class author are very responsible, you know how to clean your state, and so you implement some set of methods that, JVM, please use these to clean my state. Well, problem is your class references some other object that hasn't implemented those methods. What do we do with that? Do we null that field out? Do we maintain it and hope that it's okay? Or what if your class has implemented these methods and his class has implemented these methods, and now we're doing some kind of traversal to find objects? Which order do we visit them in? Does it matter? If we clean you based on the old state of the other class, and then we clean him based on your new state, do we end up with a consistent set of object links? Maybe, maybe not. Maybe we have to keep iterating until we hit some kind of fix point. little scary. What about threading? What if we are trying to figure out when to run these hooks? Do we pause your application to do this and run in some kind of single-threaded mode? Oh, well, that sounds a lot like Loom in dealing with pinning. Well, Loom spent a lot of time trying to figure out how to deal with VM locks and deadlocks across things and when to pin and when not to pin. And now we're introducing a whole new set of potential deadlocks into this. Can you start a virtual thread when you're in this single-threaded mode? Can you call some method that happened to use wait and notify, or something that's waiting on some other lock that's held by some other thread that's now paused in this mode? What else is the rest of the system doing when we're running this? There's really no clean answer on how to take the object heap and make it, useful and safe. Now, it's not to say that we're not trying to find things to do here, but as a general, just take the heap and use it, it's not the answer. Okay, so we need to record our observations. We need to use those to drive the optimizations we're going to do. So what do we do at the end of our training run to get those? And funny enough, we basically take a snapshot. Now, the difference is the snapshot that we take is a snapshot of VM state. And it's not a full snapshot of VM state. It's based on some of the things that we've learned over the years doing CDS. And CDS has learned a lot about how to clean VM metadata, like classes, and how to clean some of the other data that we need to be able to reuse it from run to run. So when we use when we end our training run, whether it's the 3-phase workflow from JDK24 or the new 2-phase, we generate our configuration file. And that configuration file is basically a primordial AOT cache. It's not usable as an AOT cache, but it has just enough information to be able to record the important pieces of state that we need to run to drive our optimizations. So this has our class metadata in a linked state. It has records about which constant pool entries have been resolved during the run of your application so that we can do that JDK24 AOTCache work. It also, as of JDK25, now has training data representing method profiles, method counters, records of compilation decisions, and class initialization dependencies that we need to be able to say when a profile applies well or when we're ready to compile something. So we start recording this information using the classes that we had. Now, because we've maintained the identity of the classes, we know that this profile applies to that class. So we've maintained that strong identity to be able to not have to do some terrible fuzzy matching. This primordial cache is our source of observations, and it lets us do our speculative optimizations. But there are no objects in this primordial cache. So we've got a snapshot of some of the state. What do we do? It seems like maybe that's all we had to do. Why do we still need this assembly phase? So during our assembly phase, we basically start the JVM again, just like a normal startup. Execution runs with JNI create Java VM just like it would normally. And it runs up until just about the point where it would return to the caller. And the caller would then typically go off and look up the main method and run that. But we don't do that. We stop just before that point. But on the way there, we've done the normal pre-main processing that we would do. We load the classes from that primordial AOT cache. We get them loaded, we get them linked, we get ready to go. And we apply the training data because we want that training data to be ready and live in our system, those method profiles to be ready for us when we're ready to compile code. So it's almost like a recursively solved problem. We create a cache to be able to create a cache. But the first cache that we create doesn't have all the pieces that we need. And at this point, now that we're almost ready to give control back to the user, this is where the assembly process really takes over. It does things like building the module graph. Building that module graph takes time, and it's represented as a bunch of objects. So we want to get that graph built, but we want to get it built in a clean state. So we do that during our assembly phase. We also go along and we look at which constant pool entries were previously resolved, and we resolve those, because that involves creating a whole bunch of objects, like strings. We also execute bootstrap methods for specially trusted invoke dynamics, and that may generate more classes and may give us other strings and other things that we need to persist. And so what we end up with here is a slightly larger set of classes than when we started. All right, so now we've got all this state sort of loaded up and ready to go. What do we do now, right? Do we just start to run your program? No. Now, we have all this state, but it's in kind of transient runtime state again, right? We're back to our scrambled eggs. So again, we have to go back, and now we have to do another pass where we write this out into a durable AOT cache. We want that cache to be set up and well factored so it's able to be quickly loaded for our deployment runs. If we didn't set it up correctly, we'd end up with problems where we did a bunch of work that we can't benefit from. The other thing we have to make sure that cache includes is a bunch of validation code. We need to make sure that the training data that we're loading in matches the set of assumptions and set of command line options and the layout and sizes of the data structures in the VM that we're going to be using. If the sizes don't match because you took an old cache and put it with a new VM, we may run into problems trying to process that data. All right, so once we've got this all together, we can start to write it out. We write out the classes and the metadata, we write out the set of objects that we need, so we have a heap in there, and then not yet in JDK 25, but in our Leyden EA builds and in our Leyden repo, we will then generate code. And the reason we do this sort of as a last process is because the code needs to know sort of the addresses that are being used, sort of the final addresses and the relationship between them when we write out this code cache. We've talked in previous talks about the way that we do the code. We compile multiple versions of the code, some of it with initialization dependencies, so it's safe to always run, and some of it is the optimized C2 code. But I won't go into all the details of that. I'll touch on it a little bit later in where we're going next, but this is sort of what we end up with. So at this point, we've taken the observations from our training runs, we save them as a primordial cache, we've built a clean and proper cache, including object state and potentially some AOT code, and now we're ready to write that out. But I earlier said that the object heap is toxic. And now I'm saying, well, we're persisting objects. So which is it? Well, it's both. And the challenge is that every class that ends up in that AOT cache has to be specially managed and specially monitored. And let's take a look at an example that shows why this can be a problem. So every class that ends up in the cache has to be in an initialized state, or every class that has an object that ends up in the cache needs to be initialized during the assembly phase. We don't want to reinitialize things. So every class that's initialized during the assembly phase has to be very carefully managed and has to be very carefully monitored. If we don't, we're going to end up with inconsistent results. So what I have here is 3 classes, and it's a trivial example, and you're looking at it and you're probably saying, nobody's ever going to write this code. And you're probably right, but they're going to write variations on this code that end up looking very similar. So we have 2 classes, A and B. Both of them use a third class to go and do some operation that gives them back a string. And because they don't want to keep going back and doing that operation, maybe they're scared it's expensive, they cache it. The class they go to, string setter, uses some random number it generates to cache that as well, so it can figure out what string to give you. None of this seems surprising or particularly bad, it just is. Now, as long as we run all 3 of those classes at the same time, we're going to get consistent results. There's no world in which A and B are going to end up with different strings. Except, if we start to initialize things in our assembly phase, we may introduce problems. So if we do them all at runtime, as we normally do, we get consistent results. If we do all 3 of them in our assembly phase, we also get consistent results. Interestingly, though, those consistent results have removed the randomness. So we get consistent results across every deployment. So my first deployment, if we ended up returning B, is always going to be B, and then the other deployment is B, and the other deployment is B. So everybody, we may as well hard code the value at that point. And so we've removed that. Who knows, is that correct? The only person who can know or tell is the author of that class. It's very hard for us as a JVM to say, we remove that randomness, but that's okay. All right, so what if I just initialized A early and I allowed string setter to be initialized or reinitialized later? Well, now I end up in an inconsistent world. Same thing if basically at any point, if A and B are not initialized at the same time as string setter, we end up inconsistent. If string setter is initialized early, we remove the randomness from this and we become very deterministic, which may or may not be what we intend. So we end up with something that looks like this. You say, this is stupid. Who's going to write this code? There is a particular case, and I'm a little fuzzy on the details, where I think it's list.of returns an identity, or returns an implementation class that caches the implementation. And if you, in your size check, if you are equals to the cached one, you are a list of length 0. If you are not, you are a list of length 1 containing null. So if by chance you happen to persist a list.of instance and you don't properly initialize the implementation class, your list that at assembly time was a 0 length list, at runtime becomes a 1 length list. Is that okay? Don't know. Probably not, or probably not what you meant for your program to mean. But it's very, very easy for these things to be decisions that are based on state that we don't want. And it's very easy for those decisions to seem to wash away because there's enough variations and loads through different pieces of code that it's very hard when you're looking at class A or B to be able to say, oh, this really is safe or not safe without analyzing every class that it touches and every method that it called to get there and every class that those methods touch. So you end up with this long wave of state that you have a hard time reasoning about. Okay, so hopefully I've scared you a little bit about class initialization. We still want it, and that's the challenging part of this, is that we really do want to be able to figure out the right way to initialize things, but it's not a simple problem. It's not a quick fix. Okay, so where are we going with Project Leyden? At this point, hopefully you understand a little bit more about how the assembly phase works, why we use the assembly phase, why the process that we build works the way it does, and how we're able to use that to drive some of our optimizations. The biggest takeaway from that section, hopefully, is two things. One, an understanding of the invariant that we're trying to maintain throughout the Leyden work, that we should produce consistent results between training and production runs. And hopefully that you're a little bit scared of any solution that tells you to easily just cache the heap. All right, so what are we working on? Well, we've mentioned ahead of time code compilation. We have this in our Leyden repo and in our Leyden EAs. And we're able to generate code based on the profiles that we collected, based on the classes that we have loaded in our AOTCache, and we're able to use that to drive further optimizations. So I'm not going to go deep dive into what we do for the AOTCache. That's a whole, or the AOT code, that's probably a whole nother talk on its own. But it's the obvious thing that we are working on and we are working to deliver. But it's not just the pieces we've talked about. There's a lot of other pieces that go into compiled code to be able to use it effectively from an AOTCache. I've mentioned that we compile multiple kinds of code. We have the kind that's immediately applicable. We have the kind that more closely matches the top C2 code. And now you have some transitions between those. So we've effectively added new tiers to our tiered compilation policy. And we need to do the tuning and heuristic work to figure out when do you transition between those tiers. And if the top level AOT code does not perform at the same level as the top level JIT, at what point do you want to do a top up recompile to get to that same peak performance? Maybe you're okay with a gap, maybe not. Maybe there is no gap for your application. But if there is a gap, then we also want to investigate that and see what we can do to continually shrink that gap. So there's a lot of work just in dealing with code. Now, obviously, when we start to add code into the AOTCache, we bind even more tightly to the machine that we're compiling that code for. Now we've started to select instructions like the AVX instructions or the equivalent vector instructions on the different platforms, and we start to use those in our compiled code, and then we can't run on platforms that don't have those. And so far, we've tilted our dial to bind as tightly to the local machine as you need to, and use the instructions that we have, give us the best performing code that you can. But there's another spectrum on that dial which says, like a x86 executable or an executable file, I want to be broadly applicable across common things, so detune that code as far as you can and give me something that's more portable. So these are sort of the two axes on that spectrum. And there's probably other points along there, but I think aiming for those 2 points as the sort of general mode that we want to look at and optimize for is probably where we want to go with this. The portability affects not just the JIT compiled code, it's just the easiest piece to talk about. So there are other things where we need to look at portability, garbage collectors, object sizes, heap sizes, those sorts of things. Now, we've talked about what we can do with pre-main to be able to preload and link classes, to be able to have profile data for it. But we only do that for the 3 built-in class loaders. We trust those class loaders. We know that when we tell them to load a class, we know what they're going to do. And so we're able to say, this class loader is going to reproducibly do this behavior given that set of names and this class path. So being able to persist those classes makes sense. With user-defined class loaders, we're not given the same guarantees. Your class loader could decide today is Tuesday, I'm going to go to the network and load something else when you ask for this particular name. So we need some way to cooperate with class loaders to have them opt into, I will be deterministic enough that you can optimize this. So that's one problem. The second problem with class loaders is identifying them. We said the object heap is kind of a toxic asset and collects a lot of state that we may not want to be able to carry from run to run. And class loaders are objects. They carry all kinds of state. They may have socket connections, they may have file connections, they may have who knows what that links them to somebody else. And so we need some way to be able to say, this class loader that loaded this set of classes is the same as this class loader in this run. Please preload the classes into it, or adopt those set of classes. And so there's a lot of things to figure out here. Those are just the first 2 problems, but it is an area where we're looking at how do we extend this more and more beyond the built-in class loaders. Finally, we're also looking at assembly phase class initialization. It's a hard problem. It's an ugly problem, but there isn't a whole lot of benefit in being able to do class initialization ahead of time. If those classes are initialized before we generate the code, then we don't have to worry about initialization barriers in the code that we generate. So maybe simple cases we can figure out more easily. Maybe there's some other set of cases that we have to work on, but it's still an open area of investigation for the team. All right. So, at this point, what we'd like to have you do is to pick up a JDK 24 or 25 build, take well, preferably a JDK 25 build when they ship, and go and train your application. Go and figure out what a training run looks like in your world. When you train your application, do you prefer the JDK 24 3-phase workflow, the JDK 25 2-phase workflow? Is there some other piece that if we just added this little thing that would make it easier for you to work with? Let us know. We want to be able to build the building blocks that we need to support that wide range of different deployments. So, the only way for us to find out what those are, though, is for you, the users, to pick it up, try it, test it, and report back. Figuring out how to do a training run for your application has big payoffs. It has immediate payoffs in performance improvements today for startup and warmup, and those improvements will just keep getting better as we deliver more and more pieces of this. So I think I'm at the end, and I should have a few minutes for questions.
So in one of the previous slides, I think you mentioned that Project Leyden is trying to benefit like the size of AOTCache versus the actual performance gain. Like that's one of the shortcomings of taking a full snapshot, because in the full snapshot, many things are not necessary for the peak performance. And then in the second to the last slide, you mentioned about storing assembly phase initialized classes, initializing the cache. I just wonder, like, how are we thinking about like finding the balance of the size of cache versus the actual performance gain?
Yeah, it's a great question about this, the size of the cache versus the benefit that it brings. Colleagues from Red Hat and Microsoft, I think in particular, have been working on this and being able to characterize the data that's in the cache and how much of that data that you're able to use. So they're looking very much at being able to report, okay, my cache is this big, it has these classes in it, I loaded those, I benefited from this compiled code or not. Maybe there was something that invalidated being able to load it. So there is work going on to be able to build tools to make you better understand what's in a cache and how effective that cache is in your application.
So one challenge we've had with AppCDS and also other kind of techniques to help with shortening the warm-up and startup is that these extra artifacts are non-deterministic, which is a pain when you're trying to reproduce builds bit by bit, and also creates other problems. Now, it sounds like the assembly phase is an opportunity to kind of maybe combat that issue. Is that something that's on your radar at all?
It has not been something that I've been thinking about. I don't know if others on the team have been, but it's something we can discuss further.
Please, please do. It would make this so much more usable.
What is it about reproducible builds that's standing in the way for you now?
Yeah, so like I said, one aspect is that we like to be able to produce every single bit of a build again, right? So, and then Google's build system Bazel also just gets very confused when build artifacts are non-deterministic. And that just means that it makes it much harder to use that stuff. So you can't produce them ephemerally as part of a build. You have to check them in, basically, which is a huge pain.
Thanks.
We see an interesting issue with trade-off between reproducibility and some sensitive state that may leak into the archive. For example, absolute paths on the machine where it has been created. This information, surprisingly, may be sensitive.
Yeah. Reproducibility is, there will be challenges there. So far, we haven't aimed for reproducibility yet. We've aimed for consistency. And so we should be producing the same results given consistent inputs. So if you're not seeing that, no, please let us know.
I forget what part of the elephant this was. Maybe it was like the nose or a leg or something, but how closely does the warm-up runs machine need to match your target deployment at this point? I'm thinking specifically for command line tools, right, where you generally have an artifact that's maybe just OS and CPU architecture. But I know the JIT might do something really special if you have a newer CPU or something like that. So with what we have today, we still bind very tightly to the local environment. We have recorded some of that information into the cache to make sure that we don't take a cache on one machine and try it on an incompatible machine. And we haven't done the work yet to be able to back that off. So right now, the intended workflow is it binds very tightly to the machine. Okay, so I presumably, if I train something on this here Mac and gave it to someone on a newer Mac, it wouldn't work. We would not guarantee that it would work. Okay. So we would probably discard the cache, right? The design we've taken is that the work that we do is speculative.
and speculative allows you to throw it away. So if we detect something that says these don't match, we say, congratulations, we're just going to run without the cache, and you get normal performance without it.
Just a comment about that too. You mentioned ahead of time you could generate sort of AVX 1.0, which would run across a broad set of the Intel architectures. But at runtime, it doesn't stop the JIT generating the more efficient AVX 512 or AVX2, I've lost track, AVX10 or whatever it is nowadays, when it decides to do so. So you can get a peak to warm up, and then you get a peak to peak performance as well. So that's the static dynamic nature of it all. It's really powerful.
Yeah, it's that ability to, it really is a pick both scenario, right? We can build you AOT code that's broadly applicable and then top that up with JIT compilations later if we need to. And so that's worked out really well to be able to do that.